Hello everyone. Let's introduce our project by first discussing our motivation. Our project is tied with the McGill Space Group, who would like to move away from expensive satellites towards a cheaper alternative for atmospheric research. One option is the high-altitude balloon, which is perfect for testing new technologies for space missions and to perform scientific experiments in near space.
The pressure and temperature vary a lot with altitude, which makes it challenging when selecting the electrical and mechanical components. The avionics system should be able to locate the balloon and send information to the ground via radio waves, and we need to ensure that the power supply is sufficient for a long flight.
The hardware of the system consists of 4 parts. The GPS module with antenna gets the position of the balloon, and the digital temperature sensor measures the interior temperature of the cabin. The communication system sends the telemetry down to the ground station. All subsystems are managed by the STM32 microcontroller as the flight computer, and they communicate through different serial communication interfaces.
The power system is responsible for the power generation and distribution to other subsystems. It consists of one LiPo battery supplying 12.6 volts and two DC-DC converters to step the voltage down.
The software system consists of 4 major components. The UART of the dual GPS receivers works with interrupt and saves the GPS GGA sentences. The I2C for the temperature sensor is triggered every 10 seconds, and we will convert the raw binary data into decimal values, which are then fed into the fault tolerance system. The fault tolerance system detects fault by running redundant copies of the same program and raises concerns from the comparison of results. It replicates the census reading into 2 independent thread streams, and each thread is conducted sequentially by the system. The comparator will point check the thread result and raise an error if the result comparison ratio exceeds an error threshold. The last component consists of communication thread. After waiting a certain amount of time, the communication thread will compute the encoded message of the latest GPS location and temperature data, and will send the message through the RF system. We organize testing through individual unit testing and integration testing. Each system followed a predefined set of tests before performing any integration. To test our final system, we set to run a mock flight that will last 3 hours. At all times, the receiving station will be observing the incoming messages to confirm the correct location of the system. In conclusion, this project taught us multiple techniques on embedded systems design and forced us to learn multiple tools aiding in the creation of the project. Thanks for watching.